Good morning everyone. In this class, we are going to see about this floating point arithmetic operation. Already we have started discussing about this floating point arithmetic unit. Okay, we have seen about the addition and subtraction operations for floating point numbers. Okay, and this class it's a continuation of that topic. We will see about today the floating point multiplication and division operations. Okay, and the algorithm of course. Multiplication of floating point numbers we can do by just multiplying the mantissa part and adding the exponent. Okay, so when you have floating point numbers to be multiplied, what we will do, the mantissa part, it can be either a whole integer or an entire fraction. We are assuming the decimal point position to be in the beginning or at the end. Okay, so this number must be multiplied, but the exponent part must be just added. So here no comparison of exponent is required or alignment of mantissas are required, but we do require them in case of addition or subtraction process, right? We have seen the exponents should be made equal, right? And we need to align them before doing a addition or subtraction. But in multiplication or division process, we don't require this to be done, right? And the multiplication of the mantissa part, it's done in the same way as we do it for fixed point representation. So it's the same procedure we have to follow, right? And one difference is in case of the sign magnitude binary numbers, we have already seen the hardware multiplier part. There we had a double precision result. Okay, initially if you take some n bit register, the multiplication and multiplier are n bit numbers, the product can be twice that size, right? So it can be 2n size, right? We have seen like the A as well as the Q register, both will be holding the n product after multiplication in case of fixed point numbers or sign magnitude numbers we have used for actually fixed point representation, right? But here in floating point, the precision is not an issue. We are having the exponent to handle that, right? So here a double precision is not required for the product. Here again we have those two registers, but now one of the will be holding the exponent part. So in floating point, the single precision mantissa along with the exponent will serve the purpose. Okay, so that precision is accurate enough for most of the applications. That is the only difference we have in this algorithm. So we are having two floating point numbers, both multiplication and multiplier, expressed in floating point representation. We have to multiply the mantissa part and add the exponent part. Okay, so that is the basic process. The multiplication algorithm can be divided into four parts in case of floating point numbers. First, we have to check for 0, whether the multiplier or multiplicand is 0. In either case, we need not actually do a multiplication. Anyhow, the product is going to be zeros. So straight away, we can make the accumulator contain all zeros. If both the multiplicand and multiplier are not zeros, then we can go for adding the exponents and multiplying the mantissas. So these step 2 and step 3 can be parallelly done if we have more than one adder. That is, for exponent part, if we have a separate adder, as we have seen in the register arrangement earlier, in that case we can do these step 2 and step 3 simultaneously. And finally we have to normalize the product. So if you remember what is normalization, it's actually making the most significant bit not equal to 0. And whenever we talk about here floating point, we are assuming the mantissa part as a fraction part. So the most significant bit should not be a 0 in the mantissa part. Okay, so this figure shows the register arrangement. Earlier we have seen for the arithmetic unit when you discuss about floating point addition and subtraction. It's the same arrangement, just for reference. This diagram shows the multiplication algorithm in hardware for this floating point case. And here the fixed point multiplication algorithm, which we discussed earlier, is also shown here for comparison. We just observe the two, we can see it's very similar except for this difference in the exponent part. Alright, so we start with the multiplicand in BR, start with multiplier in QR as before, and here we are checking whether the multiplier or multiplicand is 0 or not. If any one of them is 0, we need not do real multiplication. We can straight away make the accumulator content as a 0. That is, the product is going to be 0 and we'll stop the process, right? In case both the operands are non-zero values, then we proceed with the multiplication. Earlier we have seen that the multiplier is in Q register, but if you refer to the register arrangement, the adder for the exponents is between small a and small b registers. So here the Q content, small q content or exponent of the multiplier is transferred to small a, okay, and then a and b are added, that is the exponents are actually added and the result is shifted to a, okay. And the next step we can see there is a subtraction of bias. If you recall the representations we are using for floating point arithmetic, the mantissa part is a fraction part and it is represented in sign magnitude form, and the exponent part is represented using biased exponent form. We have already discussed why this form is widely used, okay, its advantage and all. If we recall, this biased exponent form is nothing but adding a positive number to make the exponent internally stored as a positive value, irrespective of whether the exponent is in reality negative or positive, okay. So for example, numerical example case already we have referred to, like the exponent range starts at minus 49 or minus 50, that number is going to get added. In case of minus 52 plus 49 is the range of the exponent in the real case. To convert it to a biased exponent, we'll be adding plus 50, so that the minus 50 will be now becoming 0, okay. So the entire range now starts with minimum value of 0 and it goes to plus 99, okay. So in this case, when you add the exponents a and b, a is also biased, b is also biased. Here now the bias is getting twice added to the result, okay, but it should be in biased exponent form, but only one bias is required. So this additional bias added now, due to this addition of a and b, that is compensated for or removed actually here, okay. Then multiplication of mantissa. So this is according to the earlier step, okay. So this is the 10.6 figure, right? So this is actually the same procedure we follow here to multiply the mantissa part. As far as the mantissa multiplication is concerned, it's the exact procedure we have followed for the fixed multiplication case, fixed number case, right? So then after the mantissa multiplication, there is a checking here done. The most significant bit of the accumulator content, that is the product mantissa parts most significant bit, is checked for whether it is a 1 or 0. So this is termed as normalization. Again, we have already talked about normalization. Normalization is making sure that, or making the most significant bit position in the magnitude equal to 1 instead of 0, okay. So we need to have a non-zero value in the most significant bit position to make use of the entire register size to have the best possible accuracy, okay. So here normalization is done. When a1 is 0, it is normalized, okay. Well, how to do normalization? The entire mantissa part should be shifted left by one position, and when we shift left to retain the value, we have to adjust the exponent. So exponent must be subtracted by 1. So a minus 1 is done, okay. A value is decremented by 1 and this AQ content is shifted left, okay. So Q is going to have the least significant part, A will be you have the most significant part of your product and it's entirely shifted towards left for normalization. Okay. In case of normalization, if you recall in addition subtraction case, we used to have a loop here. We continue this actually, right? So again we will do a checking. Okay, after doing this step, whether again a1 is 0 or 1, till it becomes 1 we used to continue. Or in addition subtraction case, we may require multiple steps of this shifting and adjusting during normalization process, but here we don't require that many numbers. Okay, why, you can think of, right? Okay, so the multiplier and multiplicand both were originally in normalized fraction. Okay, they are normalized form and they are fractions. Okay, so what is the smallest normalized operand we can have? It can be only zero point 0.1 because it's normalized. Okay, it cannot be 0.0 something, it should be 0.1. If both are 0.1, the product maximum possibility is to have 0.01. Okay, maximum number of 0 I mean, as a most significant digit. Okay, so we can have only 1 0, right? Are you getting? So if we have the smallest operand as 0.1 only, then the result can only be 0.01. The minimal value can be 0.1. So only one leading 0 may occur in this case. Okay, so at the most we need only one step of normalization. So that's why in this case we have only one step of normalization, one shift left, and there is no continuing loop as in the addition subtraction unit. Okay. Okay, so next we will see about floating point division operation. Floating point division, again similar to the multiplication, now requires the exponents be subtracted. So you know it's a division, so we used to subtract the exponents and of course divide the mantisas. And the mantissa division is done similar to the case of fixed point. And again, if you recall our fixed point division process we studied, we used to consider the dividend to be a double position or a larger number. Okay, but here in this case we have a single position, a mantissa. Okay, in both divisor and dividend are single position numbers. So with the floating point numbers we don't have this divide overflow checking. Okay, as we have done in fixed point, because in case we have a overflow we can adjust the exponent. It's not an issue in floating point representation. Okay, so actually we go for floating point to avoid this condition of divide overflow. Okay, but of course we will do one checking. If the dividend is greater than or equal to the divisor, now we, instead of printing error message or saying it's a overflow, divide overflow problem, we have to just adjust it. We have to shift it to the right and increment its exponent by 1. Okay, if already the operands both dividend and divisor both are normalized, okay, then if you do this mantissa alignment or checking, okay, so no divide overflow can occur. And this procedure we call it as a dividend alignment. So we are going to check the dividend whether it is greater than or equal to the divisor. We used to do the same step to check whether a possibility of divide overflow is there in case of fixed point. But there if you observe a to be greater than or equal to b, then we terminate the operation. Here it is not required. Instead we will do this alignment procedure of shifting the dividend by right direction once and incrementing its exponent by 1. Okay. So this figure shows the division algorithm for the case of floating point numbers. These are the steps in the process. You have to again check for zeros, of course, right? So in case the divisor is 0, it's a divide by 0 error. So we have to terminate the process. You have to say it's a divide by 0 error, right? Or else in case the dividend is 0, the result is going to be 0. So you can straight away make the result 0 and stop the process. right? So after this, after checking for zeros, we have to proceed with the real division, right? And then we start with the sign checking. Okay, so we can see here the Q is the sign of the quotient is decided by comparing A and B values, right? And using the XOR operation, this is as before done, right? So and the sequence counter is set with the number of bits in the divisor, right? And we do this dividend alignment we are talking about earlier slide. Okay, so you can see here, to have this dividend alignment, we have to compare A and B. In case A is greater than or equal to B, so we have to do this adjustment, right? The shifting A by, right by one position and incrementing its exponent part. Okay, so how to find out whether A is greater than or equal to B or not? Here we use this subtract method, right? So what is done? Checking by subtraction is used here to check whether that is comparing by subtraction is used. We are not using a comparator. So this you are familiar, right? So we have to just subtract A and B. A minus B we have to do and check the n carry. If it is 1, we know A is greater than or equal to B. If it is 0, A is less than B. So A is greater than or equal to B, then we have to do this divide and alignment. So what is that? We have to shift right A content and increment the exponent. But for checking purpose, for comparing, we have done one step of subtraction. We have subtracted B from A. So to make the values as before, bringing them back to the original values, here one step of addition is done, right? So B is again added with the content and A is updated to its original value. Okay, then we'll do this shift right of A by one position and increment its exponent. This is divide and alignment. Okay, in case A is less than B, there is no issue, there is no overflow possibility, so we need not do any alignment. But again, the value of A is restored by adding B. Okay, so then we have to do this division step. Okay, so what is division here? Subtracting the exponent and divide the mantisas. So subtracting the exponent, here we can see the exponents A and B. So B is subtracted from A. So B bar plus 1, it's nothing but 2's complement addition, or actually A minus B is the operation done. Okay, and when you do a division, we are subtracting the two exponent part and both are actually in biased exponent form. So we have added a positive bias to A as well as B. Now when you subtract, the bias component get cancelled or removed from the difference value. Okay, so to bring it back, we have to add this bias. We can compare this with the multiplication step where we have to subtract the extra bias. Here the bias is removed, so we have to add it again. Got it? Then of course A must be transferred to the small q, right? So where actually your quotient is stored. And then after this subtraction of the exponent, we have to do the division for the mantissa part or magnitude part. This again is same as the basic division process we have seen for fixed point case. And after this, the quotient will be in the QR register, right? So the mantissa quotient will be in Q and the remainder will be in A. Okay, and of course the exponent will be in the small q register. Got it?